Last time we left off right here with the famous Hubble's tuning fork diagram, which basically shows the his classification of elliptical and spiral galaxies. And so we have the elliptical galaxies. E0, remember, is the most spherical. E7 is the most elliptical. He didn't really know what to do with the S0. He thought that this was the transition between ellipticals and spirals, but it turns out that that's not the case. We'll talk about that a little bit later. And then, of course, you've got the two types of spiral galaxies. We've got just the conventional, the normal spiral galaxies, where the most tightly wound is called S sub A, and then the most loosely bound is S sub D. Again, this is pretty subjective, as to what's loosely bound and what's tightly bound. And then he noticed, some of these spirals were more elongated, and the spiral arms were coming from a bar of material, and so he called these barred spirals. And in fact, by the way, the Milky Way galaxy, our galaxy, is in fact a barred spiral galaxy. And this the same type of winding. The very tight winding is SB sub A, and then the most loosely bound would be SB sub D. And then he didn't really know what to do with these irregular galaxies. Remember, these are things that don't have an overall shape. All right, so this is what Hubble came up with, and it's still used today. The different classifications. All right, so now we're going to talk about the different content of these different types of galaxies: spirals, ellipticals, and irregulars. So as far as the types of stars, the stellar content, with spiral galaxies, you get a mixture of population 1 and population 2 stars. The pop 2 stars tend to be out in the halos of these galaxies. There are some pop 2 stars that you find within the galaxy, but that's pretty rare. It's mostly in the halos. You get the mixture of the two. This is really important as far as spiral galaxies go. On average, spiral galaxies have about 15% of their mass still in the form of gas and dust. Okay, so that turns out to be really, really important. This is the material in between the stars, right? Interstellar means in between the stars. So 15% of the mass is still, gas and dust. And what's important about that is because what that does is it allows new star formation to take place in spiral galaxies, and that is exactly what's happening even in the Milky Way, where there's still new stars forming today. Now, ellipticals are quite different. Of course, not only different in shape, but as far as the stars, they are almost always population 2 stars. So these are low metal content, right? That's what defines a pop 2 star. Population 1 stars, metal rich. Population 2 stars are metal poor. So that's the kind of stars that we find in elliptical galaxies. And in fact, the other thing, and if you think about it for just a minute, it should make sense to you. The interstellar content has very low density. In other words, there's very little matter between the stars in elliptical galaxies. Another way of thinking about that would be if there's not a lot of interstellar material, you don't have new stars forming. If you don't have new stars forming, then all the older stars that are going to go supernova have already done so in these elliptical galaxies, and that's why you don't get stars evolving to the metal content of a population 1 stars. in elliptical galaxies. Okay. All right. So irregular galaxies, these ones down here, are these are tend to have extremely young stars, hot blue stars. They have a lot of interstellar material. So the material between the stars, the gas and dust. In some cases, there can be as much as 50% of the mass of the irregular galaxy still in the form of gas and dust. So in some sense, you might think of these as lots of star formation taking place, and that's exactly what we observe in these irregular galaxies. All right, so let's see. Elliptical galaxies tend to so we'll talk about the size. You can have like really small elliptical galaxies. Sometimes they're called dwarf elliptical galaxies, and then there are galaxies that are gigantic elliptical galaxies. Some, as it says there, many times the mass of the Milky Way. All right. Let's see. Most galaxies have you get okay. I see what this is saying. Sorry. So if you just look at the nearby galaxies, that's in the local region of the galaxy. Of the universe. We see a lot of dim dwarf elliptical galaxies and some small irregular galaxies as well. And when we look at the what are called clusters, about 60%, a little more than half, are spirals and these S0 type galaxies. We think that in the early universe, galaxies were much smaller. Of course, I mean, we actually know about the early universe is because, remember, the speed of light is a finite amount. It's a great value, right? 3 times 10 to the 8th meters per second. But when you get it out into, galactic distances, well, not just galactic distances, within the galaxy as well, the further you go away from the Earth, the further back in time that you're looking. So, with our galaxy being 100,000 light years across, and we're 26,000 light years from the center of the galaxy. So we're seeing a range of different times. But then when you look out into the universe at other galaxies, you start to, when you get really, really far away, you start to go out, billions of light years. And when we look out billions of light years, and not only that is that a distance, that's also billions of years ago, galaxies tended to be much smaller than the Milky Way. All right. Now we're not sure exactly what happens. Why these, why do we get elliptical galaxies? Why do we get spiral galaxies? So we use computer simulations to try to form galaxies. We have computer technology that is able to put into motion, literally billions and billions of stars into forming a galaxy. And we find that elliptical galaxies, in these simulations, elliptical galaxies have really high star formation very early in their after their birth. So that would you have these lots of stars forming. Any stars that are big enough to go supernova will have gone supernova, and you'll only have population 2 stars, just metal poor stars. There'll be some metals, but not 1 to 2% of the mass of the stars. Whereas in spiral galaxies, in these computer simulations, we find that star formation takes place over a much longer period. And so what happens there is, in the early days of a spiral galaxy, you're going to have stars going supernova, creating metals, and then those metals, through the supernova explosion, those metals go out into the rest of the galaxy, seed the next generation of stars that will again go supernova, and that you get denser, you get more and more metal content in the new stars. New stars that form will have higher and higher metal contents, and then eventually you'll get to the point where you have 1 to 2% of the mass and the average mass of a star in a galaxy having metal content. That is, anything. Remember, in astronomy, anything heavier than helium is considered a metal. All right, so that's what happens with the spiral galaxies, and of course we have to have for the spiral galaxies, we still don't know why spirals form, but there's this density wave model and the self-propagating model as well. That's we're still trying to figure that part out. So this is just showing you some of these computer simulations. One of the computer simulations that is particularly interesting to us, not just one computer simulation, but one thing that happens in the early universe is we have galactic collisions and mergers. So galaxies can actually collide with each other, and in fact, we know that this actually happens when you look out into the universe. This picture here is just a simulation of two galaxies, and yet this picture at the bottom right here is an actual picture of a galactic, two galaxies that have merged. And we think this happened a great deal in the early universe. In fact, it's still happening. There's some evidence, there's really good evidence actually, that the Milky Way has had multiple galaxies merge with it. Like little elliptical galaxies merging with it. We even see evidence of that today. All right. So now what happens when galaxies collide, if you will? And so when we do the computer simulations, remember, the stars in galaxies are, even in the center of galaxies, are still really far apart. And so you can actually have two galaxies passing right through each other, and no stars will actually hit each other. Now, that doesn't mean that the galaxies are not affected. They certainly are. As the two galaxies get close to each other, what happens is the trajectory of the individual stars will be altered by the gravitational influence of the other galaxy, and vice versa. Right? That there's this mutual disruption in the ordinary motion of galaxies when two galaxies, the ordinary motion of stars within the galaxy when the two galaxies collide, or come close to each other even. All right. So and then we also have evidence that shows there's actually what's called galactic cannibalism going on, where one galaxy is much more massive than the other galaxy and tends to just kind of gobble up the smaller galaxy. And that we see lots of evidence of that happening right now. All right, so and just take the Milky Way and the Andromeda Galaxy. We see evidence that there's been this galactic cannibalism and ongoing galactic cannibalism right now. All right, so let's see, evidence. very distant clusters have higher proportions of spiral galaxies